Hello, everybody, and welcome to Creation Myths, where we take creation science at face value, we treat it like real science, and then we see why it's terrible. So before we go any further, I am just going to wait a second to make sure I can hear myself on YouTube and everything seems good, which it does. So I think we're good there. If anybody, as always, if anybody has any tech issues, if you can't hear me or anything, let me know in the chat. I have the chat visible on YouTube, so just call it out, and I will be able to see that. So today I have I have some fun stuff to talk about. So what we're going to do today is a responding to critics because Paul Price, Dr. Rob Carter, and Dr. John Sanford just yesterday published a new piece on genetic entropy at CMI on creation.com that is linked in the description. I think it's the first link in the description is the thing that I'm responding to. So if you want to follow along, I'm going to have screenshots of the different parts that I'm responding to specifically. But if you want to follow along in the thing, it's linked right below, and you could just follow along if you wanted. So we're just going to get right into this. Before I start, I do want to say, though, that I do plan to take questions at the end. Specifically, if there is anybody here that agrees with genetic entropy, and I see some people in the chat, and I know who you are, and I know you don't agree with genetic entropy, but if there is anybody who agrees with genetic entropy, who thinks what I'm saying is wrong, I want to prioritize those questions if anybody has them at the end, because I would love to talk about this with creationists if they would like to. So if you are a proponent of genetic entropy, stick around to the end, and I will take your questions. That's part of what we're going to do here. So that all being said, let's do this. Let's go. So a little bit of backstory here. This is actually, I was actually planning to do this stream for a few days before yesterday's piece went up on creation.com. I was going to respond to this piece, 2018 piece rather, by Price and Carter called Fitness and Reductive Evolution. I was going to respond to this piece. And by the way, I'm going to put up screenshots of like paragraphs. I'm going to highlight the stuff that matters. Don't just try to read everything I put up. I'm just going to highlight a couple things as we go. And if I don't highlight anything specifically, don't worry about it. I'll either read it, highlight it. You'll know what I want you to focus on. Don't feel like you should just read the whole paragraph. That's, yeah. Now, the reason I was going to respond to this piece is because there was a line in it, later in it, where they're talking about how some online skeptics, I'm going to use red underlining throughout to highlight passages I want, some online skeptics. And then they went on to paraphrase a number of arguments that I was specifically making a little bit before this in conversations with Paul Price on Reddit. So I don't want to toot my own horn, but I think they were referring to me there. So I was going to count that as fodder for a responding to critics. But then, just yesterday, we got this. So responding to supposed refutations of genetic entropy from the experts. And I am specifically mentioned in a number of places in this by name. So it's not a on the sly response to something I've said. It is a direct, here's this guy who has said this thing, response to something that I have said. So we're going to respond to some parts of this. Now, an interesting thing here is you see this is by Paul Price, Dr. Rob Carter, and Dr. John Sanford. They're selling themselves a little bit short in the authors there. So it's by those three. It's my understanding is it's mostly written by Price and Carter, and then Sanford, they say, contributes basically little annotations to each section. Sanford's contributions throughout this are in blue, and we're going to look at his because his are particularly entertaining at each stage. So here you can see this. So we also checked with Dr. Sanford, see if he had anything else to add in each of the following sections. He appended a note. Here are his first comments. This is the first thing Sanford says. And so now we're going to get it. This is not any specific argument. We're going to go through 3 specific arguments. They make 3 specific responses. But I just first want to start with this comment from Sanford. So the experts mentioned below are very well-credentialed scientists, yet they are not experts in the specific topic at hand, which is to say genetic entropy. This was the topic of my PhD thesis. Like, to the extent that I'm an expert in anything, it is mutation accumulation and the fitness effects of mutation accumulation in populations over generations. Like, this is what my graduate work and what my dissertation is on. So I am an expert in the very specific topic at hand. That's first. Second thing here, they have not spent the last 20 years studying the problem of mutation accumulation. Fair point. Grad school was 6 years ago, and I was in grad school for 6 years. So, okay, fair point. It hasn't been 20 years. Their 6 objections below are just off-the-cuff statements that do not seem to reflect careful consideration. I have written literally tens of thousands of words on genetic entropy. A lot of it is just on Reddit. Now, some of that stuff is off the cuff, but some of it, and I'll actually link some of my posts down below, some of it is actually long, like well thought out arguments. And not to mention, there's the section in my PhD thesis that is on this topic that I have, I think falls under the category of careful consideration, not to mention fairly robust review by other experts. So to say that this is, they naturally feel like they need to say something, but they offer only vague and dismissive comments. That's not an accurate characterization of what these critiques are, as we'll see going forward. The critiques that I'm making, that they are purporting to respond to, are extremely specific and extremely technical. And Sanford is very dismissive of these critiques. This type of response, as we'll see from Sanford, is characteristic of how he approaches this whole question. He approaches this with this air of annoyance that, like, how dare people question him. Also, I do want to point out, since they played the experts in this specific topic card, so while this is like very specifically my thing, Sanford is a retired plant geneticist and Carter is a marine biologist by training. So, and Price has no formal biology training, at least not in this. Not to my knowledge. Paul Price, if you see this, and I'm wrong, correct me, but I don't think you have any formal biology training, if I recall correctly. So to say that this is there's no experts that are specifically on this commenting is pretty rich from a lot of angles. Okay, so let's get into it. There are 6 objections that they respond to. 3 of them, they specifically mention me by name, and I am only going to respond to those 3. I'm not going to worry about the other 3. So I think it's numbers 1, 2, and 6 are where they specifically reference me in their responses. So I am going to do that. So our first one is mutations and equilibrium. And the way they do this, say objection, claim, and then a short little bit of who is doing it. Claim, as the load of deleterious mutations grows over time, the pool of possible beneficial mutations also grows with it. This eventually leads to an equilibrium, preventing fitness decline beyond a certain point. Couple things, I quibble with that a little bit, but let me keep going. This was stated by Dr. Daniel Stern Cardinal, evolutionary biologist at Rutgers University. And I do want to say, my training is as an evolutionary biologist. Right now, my technical job title is assistant teaching professor. So I just want to make sure we're clear on titles. Just make sure everyone's on the same page. Now, what I want to say here first is that this claim, I wouldn't state it that way. What this sounds like is they're saying that as harmful mutations occur, then you have more potential beneficial mutations, like just the pool of the universe of possible mutations expands, is what it sounds like, which is not how I would describe it. The way I would describe this is that as mutations occur, as harmful mutations occur, right, then you are increasing the frequency of possible mutations that are beneficial relative to prior to those harmful mutations occurring. It's a relative frequency claim is what's going on here. So I don't care for the way they state it, but that's fine, good enough. Now, an important thing to note here about Sanford's model of genetic entropy, and remember everybody, what we're arguing about here is the concept of genetic entropy, which is from Dr. John Sanford's book, Genetic Entropy and the Mystery of the Genome. And this is the idea that mutations that are harmful, but only a little bit, that have small enough effects that they can't be selected out, that these mutations accumulate over generations and eventually lead to extinction. Right? That's the genetic entropy argument, that the genome is degrading due to these mutations that are harmful, but not so harmful they can be selected out. Okay, that's the argument. If you read his book very carefully, which I have done several times, one of the things you see is that Sanford assumes constant fitness effects of mutations, right? A mutation has a certain fitness effect that's independent of things like the environment or the effective population size. And if you take that assumption at face value, right, everything has a fixed value, then this objection that there is an equilibrium where eventually you're going to hit a point where you can't get more bad, where the frequency of bad mutations equals the frequency of good mutations, that equilibrium point is a mathematical certainty. So let's look at that graphically. In this simple figure, and if you've watched my debates, I debated this topic twice actually with Sal Cordova back during the summer. This is a figure I used during one of those debates. So if you saw those debates, this is going to look familiar. What we see here on the y-axis is just represents frequency of mutations, and on the x-axis is number of mutations. Now what Sanford claims is almost all mutations are harmful, right? They're deleterious. They have a fitness cost, and almost none are beneficial or truly neutral. And even as mutations accumulate, so as you move from left to right, that frequency doesn't change. It's 99.9999, whatever, harmful, and 0.000 whatever percent beneficial or neutral. That doesn't change as mutations occur. But if each mutation has a fixed effect, then that's wrong. According to basic math, this is what would actually happen. As the deleterious mutations occur, the frequency of possible deleterious mutations slows down, and the frequency of potential future beneficial and neutral mutations increases. And eventually, at some point, you're going to hit an equilibrium point where those two frequencies are approximately equal and the genome exists at a dynamic equilibrium. That is just math. There's no actual biology there, right? That's no biochem, doesn't matter. That's just math, right? So the way that Price, Carter, and Sanford respond to this is they say that this mutation drift equilibrium is a standard part of many evolutionary models. Yes, it is. This is a pretty basic concept. They go on to talk about some other stuff and basically say that the problem is that you go extinct before you hit this point, right? Okay, you can get an equilibrium. This is a basic thing. But the point is, in order to get to that level, you have to accumulate so many bad mutations that you're already dead before you get there, right? That's what they're arguing. Now, Sanford says that this is merely dismissive, categorically wrong, and without a rational or data-driven basis. Now, that's silly because, like, as we showed, like, it's math, and you could actually do the math. I didn't show the math, but, like, people have. It's pretty basic population genetics here. And then he quibbles about the ratio of good to bad mutations. That doesn't matter. The ratio is not what matters. What matters is whether or not there's an equilibrium point. And what he's saying is that there is. He's saying it's too far past the point of where you'd go extinct to matter, but he's saying there's an equilibrium point. So, okay. I don't care how many simulations, like, I don't care about your simulations. I don't care about the relative rates. What matters is the relative numbers, and is there an equilibrium point? And if you go by Sanford's objections, his model, where you assume a constant fitness value for each mutation, independent of everything else, then you hit that equilibrium point. Okay. Now, you can see here the way he talks about this, the ratio of bad to good mutations, minimally, right? He talks about mutations as though they have a fixed fitness value. So I'm not strawmanning Sanford's model here. The way he talks about this is the way I describe his model, with every mutation having a fixed value, okay? So let's just be clear on that. So to summarize objection number one, they're conceding the math. They concede that there is an equilibrium point. They talk about lots of other stuff, the ratio of beneficial to harmful mutations, where in that trajectory extinction would happen. None of that stuff matters. If we all agree, then that the equilibrium point exists, which from what I just showed you, it seems like everybody agrees that equilibrium point exists somewhere. If we all agree on that, then Sanford's argument in genetic entropy is wrong, because he says that it's a constant accumulation with no equilibrium. So if we now, in 2020, all agree that there's an equilibrium there, doesn't matter where it is. You can think of that famous Churchill line that Churchill probably didn't say about, we've already established that, madam, now we're just haggling over the price, right? Once we establish that there's an equilibrium point, that's conceding the argument as it is stated in Genetic Entropy and the Mystery of the Genome. So that's their response to that first objection, and it falls flat on its face. So objection number 2 is that there's also an equilibrium with natural selection. Okay, natural selection will kick in after some quantity of deleterious mutations occur. You start to see a fitness cost associated with that mutation accumulation, and therefore you can have selection, because definitionally, if something is suffering a fitness cost, then it is selected against. There's the definition of the terms in that sentence, right? So that's what we're saying here. So again, this is, and again, this leads to an equilibrium. So we have, again, I'm cited here, a couple other people. The concept here that they don't name, but they're talking about, is mutation selection balance, where you get to a point where you're basically at a tipping point where the next marginal harmful mutation, doesn't matter what it is, doesn't matter what specific mutation, what the nature of it, what the specific effect is, you're at a tipping point where the next marginal harmful effect on you puts your genome over the line into the can be selected against category. So selection maintains the population right at that threshold. Anyone that crosses that line gets selected against. Anything that stays on the line or experiences beneficial mutations gets selected for. Now, just like the previous argument, this is necessarily true given Sanford's argument, because he embeds an enormous assumption in his argument that is completely unrealistic. So let's examine that. So we're going to look at 2 graphs here. We're going to look at what Sanford says happens and then what actually happens. And we know this is what actually happens, this second part right here, because we have experiments that have shown this. And my favorite example of this is Springman et al. 2010, an experiment on mutagenesis in T7 bacteriophage. It's called Evolution at a High Imposed Mutation Rate. Adaptation Obscures the Load. And we'll get to what that looks like in a second. But first, let's look at what Sanford says. So on these 2 graphs, you've got number of mutations on the y-axis and generations on the x-axis. So you just mutations over time. And then this dotted line represents the threshold of viability, basically. If you cross that threshold, you get selected against. Now, what Sanford says happens is that mutations accumulate, right? So you have your pristine genome at the start. Mutations accumulate, and you hit that threshold, and you continue to accumulate mutations, even though there is a fitness cost. And the reason for this is that, according to Sanford, in his model, everybody is affected approximately equally. So everyone's fitness, everyone's absolute fitness is declining. And the relative fitness is close enough that the differences are so slight, selection cannot distinguish between the different genotypes within those populations. Now, that's inaccurate. That doesn't actually happen. What we actually see happening is that you end up with lots of variation as mutations accumulate, because mutations are, what's the word? Random. I like to say they're random-ish, because they're not strictly random, but they're probabilistic, right? So mutations are probabilistic. Different individuals within a population get different mutations. Different mutations have different fitness effects. So not everybody hits that threshold all at once. Some individuals might hit it, and when they go over that threshold, those intolerable combinations of mutations, they'll be selected out. But the population that stays below that threshold will persist. And you could see the population ends up just settling into an equilibrium right at that threshold of viability. That basically describes every genome on Earth right now. That's where we're at. And again, this has been demonstrated experimentally. This is not something we're just making up. This is not something that just exists in mathematical models. You can do this in the lab and show and like do what Sanford describes and see, does what Sanford claims happen, or does this other option happen? And it turns out when you do this in the lab and watch what happens, the second option is what actually happens. You reach a mutation selection balance. So the response to this, the response from Price, Carter, and Sanford is that this is essentially the mutation count hypothesis that has already been answered. No, it hasn't. But Stern-Carnell also claimed that Sanford's model requires mutation accumulation without purifying selection. So first important line here, the near-neutral mutations do add up and are a factor in reproductive success. Yes, what they're saying here is absolute fitness declines. Fine, I don't care. Sure, things can get worse over time with mutations. Fine with me. As long as they're viable, they could still survive. Now let's jump down here. Appeals to natural selection, preserving the least bad genotypes, are missing the mark. The point of genetic entropy is that the least bad in one generation is actually a little more bad than in the generation before. Now that's where they screw up two ways. One, absolute fitness. How good are you in an absolute sense isn't what matters here as long as you're viable. What matters is relative fitness. How are you relative to the other members of your population? If there is variation in relative fitness, then you can have selection. Some members of a population are better than others. Or, in the way I put it, where there was the thing that I wrote that they're responding to, some members in a population are less bad than others. And you're going to see selection for the least bad genotypes or genomes within that population, right? Now, the way they're wording this, buying this least bad, more bad framing is conceding the point that there is variation in relative fitness here. Sanford doesn't acknowledge that in the book. In the book, Sanford presents it as everyone declines the same. There's no selectable variation. The way they're writing it here is different. This wording acknowledges, it concedes the point that there is variation in relative fitness, but they're now arguing a different thing, that it doesn't matter because everyone's still getting worse. But then that just gets you to the equilibrium point with mutation selection balance that I showed you on the previous slide. So they're conceding the point, and in doing so, giving up the whole argument right there. Now here's Sanford's response, and I love this. So he says that we have not carefully thought through what we are saying, and to which I say, I assure you I have. I literally wrote my dissertation on this topic, so thought about this a little bit. The nature of near-neutral mutations is such that they are not only unselectable due to environmental noise, but they're also unselectable because they are noise to each other. What he's saying right there is that you don't have any differences in relative fitness that are selectable. That's what that line is saying, right there. That's saying there's no differences in relative fitness. So as the mutations accumulate, the relative fitness of different genotypes stays close enough to equal that selection can operate. There's a lot of factors that are going to determine how close they have to be. The bigger the population, you could have smaller differences and still select for that. So there's context that determines where that selection threshold will be, but it unquestionably exists. And the fact that there are variables like the size of the population that affect where that threshold is proves that such a threshold exists, and that therefore enough variation to be selectable does occur due to mutations occurring. Now, Sanford, what he's proposing here, I just want everyone to think about this because this doesn't pass the sniff test, okay? What Sanford is proposing in his model is that random mutations, right? Random mutations, everyone gets a different set of mutations. And every individual all end up having the same net effect on fitness. Think about that for a second. Everyone's getting a different, unique set of random mutations, but that all ends up having the same net effect in everybody. So you can't select for better or worse individuals. Is that realistic? Does that make any sense in actual biological populations? I would love to ask Sanford that question because, the obvious answer is no. That's completely unrealistic and unreasonable and not how the world works, okay? So to summarize objection number 2, Sanford's model requires fitness costs to be equal across a population. You need to have 0 selectable differences in relative fitness. That never happens. That's completely unreasonable. That just doesn't happen. As long as there's variation in the relative fitness of individuals in a population. Some individuals are better than others, to the point where, because of those differences, the better ones are going to have more reproductive success than the least good ones, than the less good ones. Then you're going to have selection within that population. And the important thing here is that in that paragraph I showed you earlier, where I highlighted on the bottom, Price, Carter, and Sanford conceded the premise of that argument. And if you concede the premise, then you're going to have selection. And they conceded the premise. Therefore, we all should agree that there can be selection here. And if there's selection, that means you're going to hit a mutation selection balance. It's that simple. These are just, once you hit the first domino, it just goes. And by conceding that there's selectable variation in relative fitness, which they did, we saw that just a minute ago, they're conceding the point here. So there's a bonus here, and I love this bonus because it's from the H1N1 paper that we're going to talk about in a minute. So in their 2012 paper on H1N1, and this is from Carter and Sanford, they claimed that the H1N1 virus from 1918, they claimed that it accumulated mutations over the 20th century and went extinct in 2009 due to genetic entropy. So think about this. What they're saying is that mutations accumulated. Each individual mutation has such a small effect, it cannot be selected against. There can be no purifying selection, in other words. And this virus eventually accumulated enough mutations that it caused its fitness to decline and it drove it to extinction. There's a lot of problems with that paper. I have a whole video on it. It's linked below, and we're going to talk about it in a minute. But I just want to point out one fun line from this paper that I don't know if Carter and Sanford realize what they're doing here. But they documented a number of changes in this virus. This is a direct quote from the paper, including a declining ratio of non-synonymous to synonymous codon changes. And they abbreviate, they show you DNDS ratio. That's the rate of non-synonymous changes, i.e. changes that change an amino acid, to the rate of synonymous changes, changes that don't change an amino acid. Now, the interesting thing about DNDS ratios is you can use them to detect fitness. If the to detect selection, rather. If the DNDS ratio is approximately 1, right, the ratio of non-synonymous and synonymous is about equal, then that's neutral evolution. You're not undergoing selection. Basically, mutations are accumulating and they're not being selected for nor against. If the ratio is off in one direction or the other, you're experiencing selection. And specifically, if there are fewer non-synonymous changes compared to synonymous, so if the ratio is below 1 by a significant amount, that's indicative of purifying selection. It's selection against new variation. Well, what they're saying here, a declining ratio of non-synonymous to synonymous codon changes. What they documented right there, accidentally, I think, and potentially without realizing it, is purifying selection in the genomes that they claim went extinct due to genetic entropy, which, recall, is a model that requires no purifying selection to be operating. So they actually, in the paper that they used to claim that genetic entropy occurred, here's an actual example in Nature, they actually document something that is incompatible with genetic entropy. I think that's funny. All right, now we're going to jump to objection 6. I'm skipping 3, 4, and 5 because they don't specifically mention me in there, and other people can respond to that if they want. If you are familiar with the Peaceful Science forums, there's a thread on this, and the other people are actually responding to those things. So we're going to jump down to part 6, which is about the H1N1 paper that Carter and Sanford wrote in 2012. So the claim here is that Carter and Sanford are guilty of a fundamental error in methodology in their H1N1 research. Yes, they are. Several, I would argue, rendering it inadmissible as evidence of genetic entropy. Yes, that is a fair characterization of that claim. So this is just one person stating it. I make a similar argument that John Mercer, molecular biologist, he stated H1N1 sequences differences are falsely described as relative mutation count. The discontinuities are from rearrangement of segments, which for the viruses is called reassortment. It's where they recombine segments, which are not mutations. Calling them all mutations is grossly false and incredibly misleading, and that is true. Yeah, that is a fair critique. Basically, what Carter and Sanford did is they incorrectly documented the mutations in these viruses by comparing the wrong sequences. They used recombinant sequences, reassorted sequences, as a baseline for comparison to their ancestral sequence and used that to document the mutation accumulation. Not only that, but the one they used was actually from a completely different lineage entirely, which is fun. So there's errors upon errors here that are a problem. Now, there's tons of other problems with this paper that we're not going to talk about right now. Problems like them not directly measuring fitness, using completely inappropriate proxies for fitness. The fact that the H1N1 virus that claim went extinct is still circulating, and you could like go to the CDC website and like search for that. There's lots of papers on that they just ignore. There's so many problems with this paper. We're just going to focus on this specific thing, that they're using the wrong basis for comparison when they're documenting mutation accumulation. That's what we're going to focus on here. Okay, so here's what they wrote a little bit further down that section, specifically in response to me. This is responding to something I said on Reddit. The specific content here is not super critical. What matters is that they agree that the strain that they use as their reference sequence, as kind of their baseline for comparison, it was a 2009 pandemic strain. And in the name of the strain, it's blah, 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 2009 PDM. That's the 2009 pandemic H1N1 strain. Now, that strain was not descended from the 1918 H1N1 pandemic strain. It's a separate lineage of H1N1. It's actually descended from a reassortment of H3N2 up here. It's reassorted from an ancestral human H3N2 with avian and swine H1N1, and that's how they picked up the one variant of the H and the N proteins. It's not from the ancestral 1918 H1N1. It's a different lineage of H1N1, two separate strains, right? So Carter and Sanford and Price say, clearly we are aware of the reassortment history. Okay, great. You acknowledge that we're talking about two different lineages. Thus, the claim is irrelevant. This was known by all parties. Okay, great. We all acknowledge that there's a recombination going on there. That's good. The problem is this was not addressed in their actual work. So let's look at this. Okay, there's more here. So here's what they say. And this is a bit of misdirection on Carter's part. I believe this is Carter because it's talking about Carter doing the alignments elsewhere in this paper, in this write-up. So he said, here's a screenshot of the alignments. This is not the full thing. There's lots of other sequences here, but I cut off the picture. But this is what an alignment looks like. I've used this program myself. The bases are color-coded. You line them up so you can, do phylogenetics and calculate mutations and things. What he's saying is that this is from 1918 to 1936. See the bait and switch? He's saying, no, look, we did this right. Here's, 1918 to 1936. There is no evidence for rearrangements within the 8 segments, no reassortments, nothing going on here. This is all above board. I don't care. I'm not arguing about the alignments for the 1918 lineage. That's just missing the point. The problem is not the work they did within the 1918 lineage. The problem is using a separate lineage, the 2009 pandemic strain, as a baseline for comparison, right? You can't do mutation accumulation between two different lineages. That makes no sense. So you've got your 1918 pandemic, right? And that circulates throughout the 20th century. And then we want to know what mutations happen there. Well, how are we going to know? Well, let's compare to this other virus over here. That's a different lineage of H1N1 that's not descended from that first lineage of H1N1. It doesn't make any sense. They're just counting the wrong stuff. It completely invalidates the paper from top to bottom because everything else they do in this paper is based on that mutation accumulation finding, right? It's mutations accumulated, therefore. Mutations affected this trait, therefore, right? If you're documenting the mutations wrong, everything that follows from that is unreliable. And they completely just did the mutation accumulation part wrong. So let's look at this in a little more detail because there's a really good paper here. It's Smith et al. 2009. I'll link it in the description. This is a really beautiful figure. It shows the history of the 2009 pandemic strain, the one that the pandemic strain that everyone was afraid of in that 2009 flu year. Now, what you can see here is you've got your H3N2 human strain down here that was previously circulating. Then you've got some swine H1N1 and some avian H1N1, and then you got another one, this Eurasian avian-like H1N1. And these three strains all reassorted with the ancestral human H3N2 to get you the 2009 H1N1 pandemic influenza strain. Now, here's a question for everybody. You all see the 1918 H1N1 lineage, right? Everyone sees where that lineage comes into this system? No? Yeah, me neither, because it isn't there. Because at no point in the history of the strain they use as the basis for comparison in mutation accumulate, like to document the mutations that accumulate, at no point is this strain of H1N1 descended from the 1918 pandemic lineage of H1N1. It's two separate things. Now, in different parts of the paper, they do make within lineage comparisons. But the big picture findings that they are claiming, the big picture findings in terms of the codon bias, the big picture findings in terms of the total mutations, the differences in the rates of transversions and transition mutations over the course of 2009 or 1918 to 2009, they're using this big comparison between the 1918 strain, and we have that sequence, and the 2009 pandemic strain. It's just a completely bonkers comparison. There's no good reason to do that. It's completely invalid in terms of like documenting mutation accumulation. Now, here's Sanford's response to the critics of the H1N1 paper. You know, he says Carter can respond to this as he did above. I would just like to say that our original paper on the H1N1 virus is remarkably strong. Okay, there have been over 17,000 accesses of this peer-reviewed paper and no serious challenge to our work. There have only been a few pot shots taken at our work from poorly informed and partisan people, such as seen here. Just cheap shots. This is not like worth like a serious response. This is a dismissal. This is not like a serious response to a scientific critique of the methodology that they use. I mean, you could quibble about like my approach to like how I make these, and I'm definitely incredulous that they don't understand some of this stuff. I think there's definitely a little bit of shading the truth to make their arguments. But to say that it's just pot shots with no actual scientific basis, like you go and watch my H1N1 video on this paper. It's like it's pretty long and it's pretty detailed, and there's like a lot of specific stuff in there that I think is worth addressing. And Sanford's response is to just dismiss it, call it cheap shots, and then also get into some questionable COVID discussion here, which I'll leave that on the table, except to say that SARS coronavirus 2 and COVID-19 is real, and everybody should wear masks and socially distance until the vaccines come out. And then once the vaccines are available, everybody should get their vaccines. I don't know if other people have noticed, but there's a large overlap between young Earth creationism and COVID trutherism, which is disappointing, but not surprising. So to summarize objection 6, Carter and Sanford, they used the wrong thing as a baseline for comparison. They just used like the wrong, like they just did the comparison wrong. It's just not good methodology. I don't care if they did the alignments right. I don't care if they did them very carefully. I don't care how much that paper has been read. Like none of that stuff matters. If you're going to respond to the critique, address the critique, please, and explain why your methodology is valid instead of obfuscating. What matters, again, is that they use the wrong reference sequence for comparison, and that means their entire data set is just flawed from top to bottom, and any conclusions they draw from that data set are invalid because the data set is just, they just did it wrong at the very start. It's not more complicated than that. So they finished the paper with this closing paragraph, which I love because it's so typical of these conversations that it's just completely dismissive of the arguments instead of like approaching this as a scientific discussion. So, I mean, let's just see if any of these arguments, like any of these things hold water. First, it often takes a lot of doing to get any straight or direct answers as to why the critics, reject genetic entropy. I mean, they reference me specifically. I got like a year's worth of history on Reddit writing about this stuff. You can look up my thesis and see what I think about it in an academic sense. And also, like, I have several videos on this topic, and they're not hidden. They're like, I'm not keeping it a secret. It's easy to find why people disagree with this stuff. Second, we rarely see any evidence that the detractors have actually read Dr. Sanford's book. This is typical response. Have you read the book? I don't think you've read the book. If you haven't watched Dr. Nathaniel Jeanson debate Dr. Herman Mayes about Jeanson's book, Replacing Darwin, this will sound familiar to you because Jeanson spent a significant portion of that discussion claiming that Dr. Mayes hadn't read the book that they were discussing. I've read this book several times. My copy is highlighted and annotated. This is just a lazy argument. It seems to indicate that it's unthinkable to Carter and Sanford and Price that there might be like good faith scientific disagreements here. It must just be that the critics are ignorant of what the actual arguments are. And if we only just knew what the arguments were, if we took the time to learn the arguments, then they would be self-evidently right, and we would have to just drop everything and agree with them. No, the arguments are bad. I understand the arguments. They're just not good. And that's why I disagree with it. And, skip the stuff about have you read the book and address the arguments. Then we jump down here. Finally, it is impossible to miss the fact that even among the experts, there is no consensus as to why genetic entropy is supposed to be wrong. If you ask 10 experts why they reject it, you'll likely get 10 different answers. Often, they contradict one another. This does not mean what they think it means. This is not a defense. The fact that you can ask different people, and they cite like 4 or 5 people in this response, they cite 4 or 5 different people that have made different arguments. And the reason that's the case is because there are lots of problems with genetic entropy, and it's possible to point out lots of different problems simultaneously. You could come at it from a lot of different angles. Any one of the objections that I mentioned in my debates with Sal, for example, and I showed you a couple of the figures at the beginning here, any one of those objections is fatal to the concept of genetic entropy. There's a lot of them that are valid because genetic entropy is a garbage model from top to bottom that includes a ton, like a solid handful of unrealistic, completely just wrong assumptions at its baseline. That's why you get 10 different ways to debunk genetic entropy. That doesn't mean there's no good way to attack it. That means there's 10 good, valid ways to show that genetic entropy is wrong. Right? I think that line is funny because they just miss the point. All right, so let's summarize what we talked about here. Objection number 1, Price, Carter, and Sanford, they concede the relevant thing that there is an equilibrium, and then they change the topic to a different argument, like where that equilibrium is and what the ratio of mutations are, and I don't care about any of that stuff. Once you can see that there's an equilibrium, that's the ballgame. Genetic entropy is done, because genetic entropy requires that there's no equilibrium. Objection number 2, Price, Carter, and Sanford concede that there's variation in relative fitness, but then they contradict themselves. It seems like Price and Carter are happy to acknowledge that there's variation, but the mutations accumulate anyway, where Sanford seems more wanting to just say, no, there's no variation, everything just gets bad all at the same time. But they don't try to refute the conclusion that Sanford's model necessarily results in selection. They take offense with the parameters of the selection, but they're not saying selection would not happen. And again, that's in contradiction with the model as presented in Genetic Entropy and the Mystery of the Genome. Once you let selection start playing a role, that's the ball game for genetic entropy. Good night. And then for number 3, talk about that H1N1 paper. Price, Carter, and Sanford just miss the point entirely, or perhaps avoid it on purpose, that they're doing the most basic thing in their study incorrectly. The first thing they do is say, look at all these mutations that have accumulated. But the way they calculated that, the way they actually documented the mutation accumulation, it's just wrong. It's just like, it's a simple methodological error. Had an evolutionary virologist reviewed that paper, it would have been caught. But they didn't have someone that was like in that realm reviewing it, and nobody caught it. And here we are. It's just a basic error that anyone should have been able to catch. And nothing they said here addresses that. Now, the big picture that I want everyone to kind of come away with is that things like this, dismissive, kind of haughty, this is not how scientific discourse is supposed to work. I say this is not how scientific discourse works. Sometimes that is the tone you get, right? But this is not how this is supposed to work. If they wanted to make this a serious, like, scientific discussion. There's ways to do that. They could publish their model in, a mathematical biology journal. They could have experts in population genetics evaluate their model and see if it passes muster. They're not even attempting to do that. So what we have here instead is a blog fight where you have one of the largest creationist organizations in the world responding to Joe Schmo on Reddit and YouTube. That's not how you that's like not how you overturn the scientific consensus of one of the most robust scientific theories we have, right? And that's the case because this isn't a scientific disagreement. This is a blog fight. This is kind of a food fight at times, depending on the tone. There's not a scientific disagreement here. This is not a serious disagreement that real scientists have, right? You can find people that'll have a lot of disagreements about population genetics and fitness and neutral theory and all these other things. But genetic entropy, no, there's no serious biologist is taking this idea seriously because it, as I said earlier, there's a bunch of premises that are just silly, and we've talked about some of them here. So that's the big picture that I want you all to take away from this, and that's what I've got. So thank you all for watching this. Are there any people here? I'm just scanning the chat a little bit. It looks like everybody here is kind of on board with my critiques. Is there anybody here that supports genetic entropy and has a question? Because I would love to address it, if anyone does. My suspicion is that nobody does, but that's okay. I think everybody here is kind of on board, all 20 or so of you. So, I think that's where we'll wrap it up. Oh, I see David Neff. Is the overall genome degrading on net? I don't think so. I don't think there's, let me put it this way. I don't think there's evidence for it. So there you go. Well, there are mutations accumulating, but I don't think that's the same thing as degradation. Those are two different things. All right, everybody. So I'm gonna wrap this up because it looks like none of the creationists wanted to come in and say hi. So I'm gonna wrap this up and call it a night. Thank you all for all 20 or so of you for watching a 45-minute thing on population genetics. At night. Yeah, I saw are most mutations bad? I mean, no, most mutations are neutral. It's that simple. Most mutations are neutral. Nearly neutral, doesn't have a big enough effect to be selected. The word for that is neutral. This isn't, yeah. All right, have a great night, everybody. If you're not already subscribed to my thing, you all probably are, but if you're not already, I'm almost at 400. So give me a subscribe and a like and maybe share it a little bit when this topic comes up, because I'm almost at 400 subscribers. So that would be really cool. So have a great night, everybody. Thank you all. And I will see you all soon. And broadcast. Bye, everybody.